Our first example of interesting counter set or fractal set will be the four-corner counter set. It's constructed by beginning from the unit square, and then you remove everything except for four corners, subsquares near the four corners, and their length will be 1/4. Their side length, so on each side. And then what you do is you repeat this process as we've seen in the one-dimensional case. Once you do something, then you similarly continue. That would mean there are two ways to think about it, that you do the same procedure to this square, so you remove everything except for the subsquares in the corners, and you do this for each and every one of them. Another way of thinking about it is that let's go back and then, so you look at this picture, it's a square with four subsquares. You take one of these smaller squares and you say, I want a copy of this big picture inside that. That is, you zoom this in, you scale it down so that you have a tinier copy of whatever you see here, and then you place it in the inside of that. So that also brings out the terminology self-similar. And then you do this for every one of them. And then in the next step, again, you will look at this whole global picture after you have these corners also, and then you will place a copy of that inside each of these smaller, much smaller subcubes. Again, by general considerations, you can see that this can be described as, okay, you at every step n, you have En, which is union of some squares. So you can say these are level n squares, and how many of them are there? You can see that every time you get 4, so this will be 4 to the power n minus 1, probably, because at stage 1, well, you can ignore it stage 1 and you say, okay, already you start with the 4 squares, so that stage 1 has 4 squares in it. And then the set you're looking at is intersection of all of these. Because each En is compact, non-empty, and these are nested so that En plus 1 is a subset of En, we see that this set is not empty. It's actually also a compact set. It has properties similar to one-dimensional counter sets topologically. For example, that it is totally disconnected. The only connected components are singletons. That every point is a limit point because there is a sequence of squares converging to them. And then the set is, of course, closed, and because it's bounded, it's also compact. But as we will see, things become more interesting simply because we are in dimension 2 and not 1. To see some of the properties of the set, it's also important to look at an alternative way of constructing this set. Remember, we talked about a general way of constructing counter sets given a factor lambda between 0 and 1/2, and that was to start with the unit interval and take out something in the middle so that you are left with two subintervals that are their length is lambda times the previous interval's length, and you repeat that. So you remove something from the middle so that the remaining ones have lambda times previous steps. So you get this sequence, and then ultimately you get a counter set C lambda. We saw that the Hausdorff dimension, the only dimension I will talk about for now is Hausdorff dimension, so I don't put any subscript or anything. This is log 2 divided by log 1 over lambda. So that's a quick recall of what we had seen previously. So if you look at the construction of this four-corner Cantor set, and you only look at what happens on the x-axis, or equivalently on the projections onto the x-axis, is that you started with the full interval 0, 1, and then you are left with 1 over 4, and then 1 over 4, and in the next step again you are left with 1 over 4 times previous step, so this will be 1 over 4 to the power 2, and that's why we see that what happens on the x-axis is nothing other than c of 1 over 4. And by symmetry, the same happens on the y-axis. In particular, we see that the dimension of the projection onto x-axis of this Cantor set is 1/2. In particular, it has Lebesgue measure 0. And the same analogous claims hold for projection onto y-axis. As I said, this also gives an alternative way of looking at the construction of the set. Suppose that Kn represents the nth step in the construction of C1 over 4. Therefore, you have 2 to power n many subintervals, each with length 1 over 4 to power n. And so therefore, this C1 over 4, this horizontal Cantor set you have as the projection, is the full intersection of these Kns. If you look at the picture, you can convince yourself that the things you get in 2 dimensions following the previous construction is the same as multiplying Kn with itself. For example, here I drew K2 times K2. In the step 2, you have, maybe I should, this got shifted a little bit. Let me put these squares on perfect beginning lines. Okay, there you go. So K2 will be 4 intervals, just the intervals, of 1 over 4 to power 2 length. And then if you multiply it with itself, that means you put the same intervals in the same positions in the y-axis, and every square that is made up of these will be included here. And this is the same argument if you replace this with n. And the punchline is that with this you can see that the construction we have, the Cantor set in 2 dimensions, is nothing other than the multiplication of that a one-dimensional Cantor set. So this Cantor set in R2 is a Cartesian product of another Cantor set in 1 dimension. And we know a lot of things about this. We know it's Hausdorff dimension, and that also it has 0 Lebesgue measure. By Fubini, you can see that, for example, by Fubini, you can see that the Lebesgue measure L2 of the set E is 0, because every projection has 0. Every fiber, every vertical line cuts it along a copy of C which has 0 measures, so you're integrating 0, and therefore you have no positive measure. But actually we will see stronger claims about the set E, from which it will be immediately obvious that this set is in fact much smaller than we might think. Okay, so far we have several claims. The most important one to me in this talk is that projection of the set onto X, respectively onto Y axis, is of Hausdorff dimension 1/2. Now the next claim will be that the projection of this counter set onto the line y equal 1/2 x is a solid interval. That means the shadow of this set, when you project it onto this particular line, covers a whole segment. It doesn't miss any single point. And the proof is basically what you see in my picture. So let's look at the finite steps in the construction of this set. So you started with these 4 corner sets. Actually, this claim is easy to prove, because if you miss any point, if this point is missed at a finite step, then it will be missed forever. So if you want to prove that something, that the set, the projection of this, the ultimate set will cover everything, you have to show that every finite step will do. So let's look at step 2. We have the 4 corners. When you project it in this direction, and that explains the particular choice of 1/2, you see that the extreme points of the cubes, this here and this here, align perfectly, so that, well, from here to here, everything is covered by this cube alone. We don't care if it's also covered from anywhere else, which isn't in fact. And then the next cube begins right immediately at this point. So this point gets actually covered twice, and then the ball is passed to, if you're watching FIFA these days, to this next cube, and it covers up to this point. And then again, because of that slope thing, it perfectly aligns here, so that this cube immediately begins to fill in the rest. And actually we cover more than just what is inside the unit square. Now what happens, will this persist for future iterations? The answer is yes. So what will happen in the next iteration? So you will have these 4 cubes for this one. So you will replace these, the square on the corner with these 4 red ones. But then, because of, again, similarity, so we have to use in these types of questions, we have to use similarity as much as we can. So a parallel line to y equal 1/2x, so plus some constant, the situation will be exactly the same. So when we don't even need a proof for this, because it's just self-similar pictures. So we see that when you project these little cubes onto this line, they will cover a whole segment, and that will run exactly from here to here. But it doesn't matter if it is this particular shift of that line. So if you project in turn further down here, you get the same shadow. So the shadow doesn't change, because these are just parallel shifts. So you see that even though we will lose out a lot of space, in particular we lose the whole center, the green part, in the next iteration, we don't lose the projections because of the very unique way these subsquares are aligned. And the same argument, of course, will go for every other cube. So within every cube, the next generation does just as a good job of covering the full segment as did the original square. So then you can say that the proof will be just, it suffices to show the claim for each kn multiplied by kn. So the picture I had showed k2 and then k3 maybe steps, and that's the end of the story. We can, in particular, we can exactly compute how much this will be. This will be length from here to here. Okay, why is this significant? Why look at this particular projection other than its interesting geometry? So if you have been following the Hausdorff measure part, one of the facts about Hausdorff measure is that Hausdorff measure under Lipschitz maps behaves the following way. So if you have a function from x to y, two metric spaces, and f is a Lipschitz, then for every non-negative value for every subset of x, the Hausdorff measure of in any dimension, so S of image of the set, does not increase more than L to power S, the Hausdorff measure of the domain you started with. This becomes very interesting for the case of projections, because projections are one Lipschitz. Also, it's a easy consequence of this that Hausdorff dimension also does not go up. It could go down. You could have positive here and 0 here, of course, for example, if f is a constant function. But we're looking at upper bounds. So the Hausdorff dimension cannot increase under Lipschitz maps, in particular under projections. So in this case, we saw this map F, the projection, that is one Lipschitz, and its image has positive h1. So above, what we saw that was that h1 of the projection of this counter set onto that particular line was positive. So h1 of E itself has to be positive. This means, but it could also be infinity technically, that the Hausdorff dimension of E is at least 1. Okay. Now we look at the upper bound, but it is even easier to see that h1 of E, did I say 1? Oh, right. Okay. So we saw that this is bigger than 1, and that implied this, but also we can see that this is less than a constant. I want to say 1, but I'm also not sure, but some constant, independent of everything, which then would mean that the Hausdorff dimension of E is precisely 1, because we found out that h1 of E is positive and finite, so the Hausdorff dimension is exactly 1. But how do you show that? How do you show that h1 is no bigger than a constant? Well, getting upper bounds on Hausdorff measure is easy. It is enough to find particular coverings. So if you find just one suitable covering for your purpose, that's enough. Okay, let delta be positive. Take n large enough so that diameter of every square in kn times kn is less than delta. So definitely that happens already in this picture. You can see that the further steps you will go, the diameter of individual cubes will be very small. Then take, so you fix n, and then remember there was this I, and how many cubes are there? So we had 2 to n on the line. That will be 2 times 2 to n, so that will be 4 to n. It's even easier to see from the original description of the set where you had 4 squares replacing the previous one. So every time you multiply by 4. Then also we see that diameters of these, each one of these, ki to power n, is less than or equal to 1 over 4 to power n. Because again, every time the new squares have 1/4 the length of the previous one. But also diameter is like going diagonal in 2 dimensions, so maybe root 2. But let's be safe, root 22 maybe, the year we're in. Just to be safe, we only want an upper bound. And then we said that we want all of them to be less than delta. So you take these form, this collection of sets form a delta covering of the counter set E. Remember, E is intersection of all these kn's. So by definition of Hausdorff content, so H1 delta of E will be less than, remember that's infimum of all such things, so it's in particular less than one of these. So this will be in I going from 1 to 4 to n. This constant, so I'm already putting every constant down here, diameter of elements in the covering to power 1, because I'm using Hausdorff measure 1. So the C here in particular will be 2, but don't care again. But this is C, and each one, if we replace these by 1 over 4 to power n, so this will be a new C. We will have 4 to power n many of these, and then 1 over 4 to power n. But this cancels, and that's the point. This is independent of n. So because the right hand side is independent of n, we can let delta go to 0. So we can let delta go down to 0 to recover that H1 of E. By definition, that's the limit when delta go to 0. That also remains bounded from above by a universal constant. And that finishes the proof. So that is our second claim about this set. So again, let's summarize. Projection onto x and separately onto y-axis is of dimension 1/2. In particular, okay, so maybe actually this will now be more surprising when we start with this one. E is of dimension 1, so it's kind of, it behaves like a curve. It doesn't have area, but also it's not too much small. So it has Hausdorff dimension 1. In particular, it has a length, meaning nothing other than H1 is between 0 and infinity. But when you project it onto x and y axis, we see that H1 of the projections are 0, because projections are 1/2 dimensional, so their one Hausdorff measure is definitely 0. But then there is this projection onto the particular line, 1/2 x is a full interval. That means also of dimension 1. Remember, projection does not increase dimension, but in this particular case, we see that it did not decrease it either. So which one of these two is the more typical for this set? We have x-axis and y-axis, these particular lines. You project onto them, you don't see your set. You don't see any length. The length becomes 0 under the projection. So their shadow doesn't show any length, but the set itself does have positive and finite length. Then there is this other particular line you project onto, and then you see a lot of your set. You see a full interval. Which is the more typical one? That is something we're not going to go into, and that is why we're starting with examples, and through these examples we will discuss some properties just without proofs, so that when we present some theory, we will have a lot of examples to look back on and to draw conclusions from, or at least conjectures from. So the theorem that I found in Simon's book, the particular statement, says that if you have a condition 1 for a set, if you project onto x-axis and y-axis and you don't see anything, then for a set that has positive and finite h1 measure, then E is purely unrectifiable. So rectifiability is a key and central topic to geometric measure theory, the branch that is concerned with geometry of sets, and pure unrectifiability is kind of a negation of rectifiability. And in particular, it implies that projection of E onto almost every line, we can make this precise by parameterizing the collection of lines in R2 by the unit circle. So every line is completely determined by a point on the unit circle, giving its slope basically. So for almost every line, in the sense of Lebesgue measure, so if for Lebesgue measure almost every point on the circle that you pick, that means almost every line that you pick, the projection of E onto that will have a 0 h1 measure, so that we see the behavior 1 and not 2 is generic for this set, and in general for purely unrectifiable sets. One of the properties of those is that you don't see those sets through shadows and projections. So that brings us to the end of study of this kind of basic and yet with quite interesting properties set. If you have any questions, please put them in the comments. Some of these things you have to really do on your own to really see. In textbooks there's even less detail, and no one does these for you, at least not in full generality. They just put stuff in the exercises if there are exercises, or they just claim these. So everyone is supposed to do these calculations on their own and then see for themselves. But yeah, there we go, our first example of a fractal set in dimension 2. So any questions, please put them in the comments. I see a lot of new people coming to the channel. Please consider subscribing if you haven't yet. And until next video, have a great one. Thanks.